the cloud. What else I extremely need? Day 4. Yeah, day 4. So today we have our last last day of my part. So you will have, as far as I remember, 4 or 5 days with Dean Fantazzini. So what? So the first question is about home assignment. Okay. So where is the? Just a moment. A Google form. Pum, 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 pum. Just a moment. Just 1 or 2 minutes. Ooh. Because I've done it, but I forgot the link. It's better just to make a new one. Okay. Just a moment, because I have prepared, but I'm missing it now. Okay, just a moment. I will make a new form that will be a little bit better to find the old one. Okay, so the course we need is a course about. Sorry, I can't find the form where I have prepared all the things. But anyway, so we need a course on Arima. And this is the first course. And the second course is, sorry, because I have prepared the form, but I cannot find it in Google Sheets. I don't know. I don't know why it's not in recent. Just a moment. We need, okay, these courses. The first one is Arima, and the second one is, what the hell? The first one is Arima, and the second one is forecasting in R. So the difference in these courses is the following. This one works with all the syntax that it was before Fable. That one is, so in a break, I will find my form and will publish the links in the chat. So you have to do 2 courses before exam. 2 courses. One about Arima, and it works with time series as TS objects. And forecasting with R is about modern style forecasting with Fable package with objects of class Sybil. So I think it's good because there are some packages that use older syntax, that use new syntax. So it's a good idea to know both ways to work with time series objects in R. So basically, you need to do 2 courses, to finish 2 courses before exam. Basically, that's all about home assignment. I will find, or I will just create a new form in a break. So you just put there your true name and your DataCamp registration mail. You can use any mail for registration, and I will add you to the group with free access for 6 months, and basically that's all. And to recall that, so you will have 2 questions, 2 questions from me on the exam. one will be about forecasting with ETS model, and the other one will be forecasting with Arima model. On the exam, you will have 2 questions from me, and other questions will be from Diane Fantazzini. So basically, that's all. Sorry for missing form, but I will publish in the chat.
Could you repeat, please? The deadline for the homework is?
Exam day.
Exam day, and it's in June.
I'm not sure that in June. The course is too short. I'm not sure whether it's in June. Why it's in June?
Well, I thought it was about it lasted 2 modules. No,
you are wrong. I don't know the exact date yet, because the exact date is set in accordance with the study office. But I'm pretty sure that it's not in June. So the course is very short. I think you will have 5 or maybe 4 or 5 or 6, something like that, lectures from Diane Fantazzini. So imagine 5 full lectures is like 1 month and a half. So if you add 1 month and a half to current date, you will have the 1st April, something like that.
Okay.
So I don't.
Works for me.
That's not in the. That's certainly not June, but I don't know the exact date. So for me, before exam, I will, because I will need to check your exam, and when I will get your exams, I will check on that day who has completed the courses. If I have completed the courses, so you have done your home assignment, my part of your home assignment. And one important maybe notice that I don't care about experience point, or so only. So on data camp, you may use hints for free. So if you are unable to solve some exercises there, then you can just click hint, one more hint, one more hint. That's okay, because when you are studying programming, that's a normal way. You are searching the web, so um, so you are not. So I don't care about experience points. So there is a gamification aspect of data camp, and basically you will receive less experience points if you use hints. But for grading, I do not use these experience points at all. So basically, you may use all the hints you want and get 10 out of 10 for your home assignment. Okay, so I don't care about experience points. So for me, if you can pass the course without hints, that's perfect. If you can pass this home assignment with the hints, that's perfect. So maybe the is so do not be afraid to use the hints. Okay, so I think it's about something 1st April. So, but I'm not sure, but it's certainly not in June. So maybe even before, but normally it's the end of this module. Okay. So what about Harimo model? Basically, I hope that some of you know about Arima models.
They are integrated Arima models.
Yeah. Alexei, I don't mean your idea 7 courses on data camp. What do you mean? I've seen your message in the chat. There are 7 courses on data camp. There are a lot of time series courses on data camp. You have 7 courses, but that's great that you have 7 courses completed. That's a good achievement. I don't see a point for the moment. If you have already done these courses about Arima and forecasting in Arp, then that's perfect. So you just do not do anything. You are just fine. If you have already completed these 2 courses, then that's great. I have nothing against if you have already completed them before. Okay. So let's go on with Arima models. So I would like to start. So let's start with non-seasonal Arima model, then with seasonal Arima model, and then we will estimate. So we will speak about these models with pen and paper first, and then we will move on to R, because in R, that's if you know the design of a Fable package, and it's easy. You just replace ETS by Arima and you are done. So basically in R, there is nothing important to discuss, but on pen and paper, I would like to recall some important points. So first, let's speak about Arma model, Arma PQ model. One of the important points that I would like to stress, that many authors confuse time series stochastic processes with equations. So there is a big confusion in even in good sources. There is a confusion between equation and solution. That's a very important confusion in many sources. It's pity that even good sources sometimes do mix these 2 concepts. Okay, I will try to explain first this confusion, a big confusion in literature. Let's imagine that I have a white noise. Let's imagine that UT is a white noise. Short recall, what is a white noise process? What do we expect from white noise? Who is with me?
IID, expected value equals 0, and the variance sigma squared finite.
Yeah, you are more or less right. The variance is constant, expected value is constant, covariance is 0, at least for different moments of time. It's not required that they're independent, it's too strong. So when you say they are independent, they may be, but they may be not. You will study an example of Garch processes. Garch processes, they have 0 covariances, but they're dependent white noise processes. So basically, if they are independent and identically distributed, it's a white noise, but not vice versa. So the requirements are at least a little bit less than you stated, but in general, you are right. Okay,
yeah, thank you.
UT is a white noise process. When I write something like this, YT is equal to, let's say, UT plus 0.5 UT minus 1. So it's a tradition to omit, so because this point of mathematics is widely used by guys who avoid rigorous math. So the normally confusion, so that's not important. Normally that we admit that this equation works for every t. But it's okay. If you omit, no one will blame you except some very rigorous mathematicians. But normally, you should mean that I have written not one equation, but I have written a lot of equations. y2 is equal to u2 plus 0.5 u1. y3 is equal to, and so on. So it's okay. And I think that yt, like I'd like to have an expression for yt. And there are no ambiguity here. Yt is equal to ut plus 0.5 ut minus 1. But if I write a little bit more difficult equation, if I write something like this, yt is equal to 0.5 yt minus 1 plus ut, and I say that for every t. So in this case, so this is the case A. Let's state clearly the distinction between case A and case B. Yt is completely determined, completely described, and described in terms of ut. And in this case, you can ask some, so usually in some books, you may find a question like this. You have an equation like that, yt is equal to 0.5 yt minus 1 plus ut, and some question is yt stationary? Is yt stationary? Yeah? Who knows the answer? Is yt stationary?
Yes, it is stationary.
Why?
Because the R part is invertible. Because this process can be expressed by ma of infinity expression. Thus, it will have finite expected value, finite variance, which will be the same for every observation. And the covariance will depend only on the lag parameter.
Okay, that's a popular answer. Yeah, in many books you can encounter this wrong answer. You're right. You are. I expect that you were taught like this. Your teachers have told you that that's a stationary process. It's wrong. It's a very popular confusion in literature. I will explain you why in 1 minute. So popular.
Isn't because of the coefficient that in modulus is less than 1?
Yeah, it's wrong condition. It's a wrong condition. I will explain you in a moment. Popular but wrong answer is yes. 0.5 is less than 1, so yt is stationary. It's wrong but popular answer. In many books you can encounter this wrong answer. So now I will tell you the truth. The correct answer is yt is not specified by this equation. We have no processes. We have no process here. We have an equation. Equation is not always a process. So imagine that I will provide you y0. Example. Well, you have yt, that is 0.5 yt minus 1 plus ut. Ut is a white noise. And I say u0 is 42. I just like 42 as a starting value. What is the expected value of y0? It's 42. What is the variance of y0? It's 0 because y0 is 42. What is the value of y1? y1 is 0.5 times 42 plus u1. It's 21 plus u1. What is the expected value of y1? It's 21. What is the variance of y1? It's variance of 21 plus u1, and it's sigma squared u. So if you like, what is u2? y2, sorry, y2 is 0.5 times 21 plus u1 plus u2. It's 10.5 plus 0.5 u1 plus u2. What is the expected value of y2? It's 10.5. What is the variance of y2? It's 0.5 squared sigma squared plus sigma squared. It's 1.25 sigma squared. And I see that if I add one condition, I receive a non-stationary process. Why it's non-stationary?
Wait, you're talking about the predictions.
No, I'm not talking about the prediction. I'm talking about the process. My point is that this is equation. And if I speak about equation, let's call it equation star. If we talk about equation star, this equation does not completely define a process. Only if I add initial condition, it will define a process. And the stationarity of a process will depend on the initial condition. I have added this initial condition. And given this initial condition, expected value changes over time, variance changes over time, and so the process defined by equation plus initial condition, the process is non-stationary. So the main point that is often omitted in many books in just like a solution or stochastic process is difference equation plus initial condition. And if you have only difference equation, like in my question, I have only difference equation, stochastic difference equation. If I have only stochastic difference equation, then the question, is yt stationary? The correct answer, it's not a process yet. If I add one initial condition, we see that it's non-stationary. I may add another condition. So let me add another original condition, initial condition. So if I consider the same process, but like this, yt 0.5, yt minus 1 plus ut, the same equation, but let me add y0 is 0. So in this case, what is the expected value of y0? Is 0. What is the expected value of y1? It's 0.5 expected value of y0 plus 0, and it's also 0. What is the expected value of y2? It's 0.5 expected value of y1 plus 0, but we have proven, and by induction, we can say that expected value is always 0. So this is difference equation. And this is initial condition. And if I take y, but let me check whether it's stationary. y1 is 0.5 times 0 plus u1, u1. y2 is 0.5 times u1 plus u2. And if I check variance of y1 is sigma squared, and variance of y2 is 1.25 sigma squared. Is my new process stationary? Woohoo! Anyone?
It seems like not,
Wow.
because it should be the
No.
same.
Yeah, you're right. Non-stationary is not stationary. And finally, if I provide a very special initial condition, if I get the same equation and I provide initial condition y0, once again, the same difference equation. I have not changed it at all. Same equation. But I have a very, very special initial condition. Indeed, it can be proved using complex analysis techniques that it's basically the only choice, almost surely only choice. So one very special initial condition that it should be u0 plus 1/2 u minus 1 plus 1/2 squared u minus 2 plus 1/2 power 3 u minus 3, and so on. So if I have a very, very, very special initial condition, very special initial condition, then a very special initial condition. And if I plug in, so what expression for y1 I will get? I will get, so let me put this special initial condition into my difference equation. It will be 0.5 times u0 plus 1/2 u minus 1 plus 1/2 squared u minus 2 1/3 1/2 power 3 u minus 3 plus u1. And if I open the brackets, I will see that I have a miracle, the same structure of ut in terms, or the same structure of yt in terms of ut minus 1 and so on. Y1 will be 1/2 u1 plus 1/4 u minus 2 plus 1/2 power 3 u minus 1 plus 1/2 u0 u minus 1 u minus 2 sorry, that's like this. Yeah, I think like this. Okay.
Yes, seems correct.
Yeah, and now I see that because of the same, exactly the same structure, by induction it can be easily seen that y2 will be u2 plus 1/2 u1 plus 1/2 squared u0 plus so on. So I see that the structure of every y is the same. It's a linear combination of past ut minus 1, and in general yt will be ut plus 1/2 ut minus 1 plus 1/2 squared ut minus 2, and so on. So and because of the same structure, I can see that expected value of yt is 0. I can see that variance of yt is constant. Why it's constant? Because I will basically calculate sigma squared plus 1/2 squared sigma squared plus 1/2 power 4 sigma squared plus so on, and it will not depend on t. Yeah, it will be constant. It will not. It will be constant. Constant will not depend on t. And that solution is stationary. So my first point, I would like to remove that confusion, because many even good authors, you may
Wait,
find.
but we can receive this solution just by inverting the Arp process.
How?
Using using leg operator and then divide
And
it
why
to
you can invert? Why you can invert? If you have an equation. So my main point of view, my main point, that if you have an equation, you have an equation, yt 0.5 yt minus 1 plus ut, then first thing you should know, it has infinite number of solutions as a first point. If you have at least if this equation has at least one yt minus 1 or yt minus 2, and it has infinite number of solutions. The second point is that it has infinite number of, so let's speak about not this equation, because this is too particular. I will speak about general Arp type equation. So let's speak about the general autoregressive equation. It's not yet a process, it's equation. It's equation like yt is equal to some phi1 yt minus 1 plus phi2 yt minus 2 plus phi p yt minus p plus ut. Ut is a white noise. And so this equation is, for the moment, it's only equation. And first point, it has infinite number of solutions. I assume that p is greater than 1. If p is 0, then it has only one solution. Okay, so almost all these solutions are non-stationary. It has 0 or 1 stationary solutions. Almost, if I consider that solutions are equal, if they are almost surely equal, is considered as the same solution. So, and the next maybe new thing that you will learn, that maybe we just confused, and instead of saying that the process is stationary, we need to say equation has a stationary solution. But I will maybe shock you that one more news will be shocking. Not only this is not a process, this is an equation that has infinite number of solutions. That the third shocking news, that it has a stationary solution, one stationary solution, if and only if, who can continue? It has a stationary solution, it has one stationary solution, if and only if what? When does Arp equation has a stationary solution?
when all the roots of the characteristic polynomial belong outside the unit circle.
Yes, and this is wrong. That's a common misconception that is in many time series books. You will read the same misconception.
Wait, are we talking about the weak stationarity?
Yes, we are talking about the weak stationarity. Yes, and what you are saying, it's a common misconception encountered in many books. That's not your fault. I'm not blaming you. I'm blaming these authors who are just copying the same wrong statements from one book to another. If you'd like to have a book written by a good guy with a good mathematical background, so you may read say, you may read odd, then var, and basically that's a very small pool of books when the authors clearly state that this is wrong, what you are doing, because the same wrong idea is copied. So, okay, it has one stationary solution if and only if all lambdas are, lambda is the root of characteristic equation, when all lambdas are not equal to 1. And to convince you, I will show you a stationary solution when the root is 2. So, example. It's not a proof, but I think this example will convince you that the theorem you are mentioning is wrong. Okay, let's consider the following example. Yt is 2 times yt minus 1 plus ut. Ut is a white noise. White noise. And now I will do a miracle. Now I have nothing. I have no hidden tricks. I will just show you, provide you a stationary equation, a stationary solution. So
yeah, we're waiting for it.
Yeah, I hope so. So this equation has a stationary solution. Okay, let's do it. Let's find it. So yt is 2 times yt minus 1 plus ut. I will use your idea. So basically, you would like to say, imagine the solution is stationary. Yeah, imagine that equation is so imagine some solution yt is stationary. So basically, what we can conclude from stationarity, we can conclude that if I take, for example, limit of expected value of 1 over some a yt when a tends to infinity, so this limit should be 0, because if I assume weak stationarity, I will also assume weak stationarity. So the expected value of yt should be less than infinity, and if I divide it by a very big number, I should get 0. Variance of 1 over a yt when a tends to infinity should be, this limit should be equal to what?
Sigma squared?
No, I divide by a very big number. You are right that without a, yeah, you are right without a, but I have an a inside formula.
It should converge to 0.
Yeah, it should converge to 0. Right? Why? Because I divide sigma square. You are right that you mentioned sigma square. Yeah, without this part, that should be sigma square constant, but not in this case, because I divide by a big number. Okay, so let's remember these two conditions. I rewrite this equation. So because it's work for every t, then I can write that 1 over 2 yt.
Wait, but these are not the only conditions that we need to prove.
Yeah, no, yeah, you are yes, and I have I have a implication in one direction. Yeah, you are completely right. That's not the only requirement.
Okay, let's go on.
So I divide by 2 and get 1 over 2 yt equals to yt minus 1 plus 1 over 2 ut. So I have yt minus 1 equals to 1 over 2 yt minus 1 over 2 ut. And let's plug in. Let's use the same equation. So yt is 1 over 2 yt plus 1 minus 1 over 2 ut plus 1. I've just changed the time index. And then I will plug in yt plus 1. I will use your technology inversion of a lag polynomial, how you call it. It's possible with stationary solutions. You're right, but you can use this technique if you assume that the solution is stationary. So yt is 1 over 2, but what is yt plus 1? It's 1 over 2 yt plus 2 minus 1 over 2 ut plus 2 minus 1 over 2 ut plus 1. Okay, now I have minus 1 over 2 ut plus 1 minus 1 over 4 ut plus 2 plus 1 over 4 yt plus 2. And I plug in yt plus 2. And I will have minus 1 yt plus 1 minus 1 over 2 square root ut plus 2 minus 1 over 2 power 3 ut plus 3 plus 1 over 2 power 3 y t plus 3,
Plus
I think.
3, yes.
Yeah. And I continue. And this term will have a higher and higher a in denominator. It will be 2, 4, 8, 16, and so on. And basically, when I will take limit, I will get yt if I assuming that yt is weakly stationary, I will get that yt is minus 1 over 2 ut plus 1 minus 1 over 2 square root ut plus 2 minus 1 over 2 power 3 ut plus 3, and so on. And basically, you can check that this is a solution. This is a stationary solution of this equation. It's a stationary solution of the equation yt equals to 2 yt minus 1 plus ut, where ut is a white noise. And that's a common misconception. I have encountered a lot of bachelor courses when installed. When the coefficient is 0.5, when the process is stationary. The first point that is wrong. It's an equation. It has infinite number of solutions. It's not a process. That's the first lie you have encountered in.
Wait, but
yeah,
we use some kind of inversion here. And the problem is that this solution is pointless. It's completely useless.
No, it's not pointless. It's not at all pointless. It looks in future y, in future u. And if you'd like to interpret that ut is a, so you have problems with interpretation using this solution, but it's not completely useless. For example, if I would like to recover missing point in my time series, then my recover. So if I have, it's not completely useless. You are wrong. Just accept that this equation. So we need to state correct theorems, and we need to. So my point is that theorems should be stated carefully. You cannot just look and say, "Oh, equation is a process is the same thing." No, equation is and a process are not the same thing. One equation can have infinite number of solutions, and it can. And if you are speaking about stationary solutions of an equation, then sometimes you have a stationary solution that looks into the future. And if you'd like to state a theorem correctly, you should say something. Yes, equation has solutions that are stationary, but I'm excluding solutions that look into the future. Okay, you may do that point, but even in this point, even if you accept this approach, so you may say like this, you may say the following theorem. So let's consider IRP type equation. I clearly state that it's an equation, and indeed you are right that you can say if all lambdas are less than 1. So it depends on what are you calling characteristic equation, but let's call characteristic equation. So there are different approaches. I have used one approach when I told a course on Coursera, but I've discovered that this definition of characteristic equation I have used on Coursera is not so widely accepted that the converse one. So I will, if all lambdas are less than 1, by characteristic equation, I mean lambda to the power. So let's have an IRP equation like yt is phi1 yt minus 1 plus p yt minus p plus ut, and by characteristic equation I mean lambda to the power p equals to phi1 lambda p minus 1 plus lambda 2 plus p2 lambda p minus 2 plus p times 1. By characteristic equation, I mean this one. And if all lambdas are less than 1, then ARP process has a ARP equation has a unique stationary solution that has one more property. Yt is expressed in terms of past ut, ut minus 1, ut minus 2, and so on. Plus, I don't know, alpha 1, ut minus 1, plus alpha 2, ut minus 2, plus, and so on. And if so I will just write all the statements correctly. So this is the statement you would like to say. You need you need to specify that if all lambdas are not equal to 1, then ARP equation has a unique stationary solution. And the third point, it always has infinite number of non-stationary solutions. You may always say, I'm never interested in solutions that look into the future, and you are wrong. For example, if you encounter a problem when you are trying to reconstruct missing point, and it happens, sometimes you need to reconstruct missing points in your time series. So if you have, so you will say, I'm always interested in, so that's so I will never use second point. But we may say, if you have a time series that goes like this, you have some points, then you have some missing points. Believe me, when you will forecast, or maybe it's better to say reconstruct these points, believe me, it's better to use that part and that part. And in this situation, you will use, so in forecasting, but it's not forecasting, it's reconstruction, yeah? But in reconstructing this part of the process, you will use past U1, U2, UT minus 1, and future UT. And you may say, how am I able to reconcile? So, and in this case, your forecast, your reconstructions will depend on past and on future. And that's okay. It's a real problem to reconstruct missing values. So my first point is that you need to say a lot of not so good books on time series. On the internet, you can find a lot of simplifications. That's okay, because these sources may give you good ideas about forecasting and so on. I do not blame you or these sources, but to make some progress, we need to accept the idea that an equation, first idea, an equation has a lot of solutions. Some of them mostly non-stationary, but it has one stationary solution. Not when all lambdas are greater than 1 or less than 1 by absolute value, but they are not equal than 1. And the second point, if we add one more additional condition, that we are searching for stationary solutions that depend only on the past. In this case, yes, it will be a good theorem that we have that this equation has only one stationary solution that depends only on the past values. Okay, is it better like this?
Yeah, I think yes.
Let me add with structure of the form. Yeah, it's better to add of the form. But my main idea that an equation without initial condition or without some additional statements is not a process. That's the first point. The second new idea for you that it has a unique stationary solution, not when all lambdas are less than 1 by absolute value, but when all lambdas are not equal to 1. And this additional requirement that all lambdas are less than 1, this additional requirement guarantees that the solution will be stationary, and it will not depend on the past or on the future. It will depend only on the past values of white noise. It's a very popular misconception, and my mission on this planet is to tell you the truth. Okay, let's move on. So the problem with, so we have discussed a little bit autoregressive processes. So an example will be, so basically when a process is estimated, it's assumed that we are searching for, so when a process is estimated, it depends on the method. So for example, I can provide you an estimation of a process, and I may have there in the result where is lambda is greater than 1. But in many statistical software packages, by default, when we estimate ARP process, it's assumed assumption, implicit assumption, when you require, so when you launch, for example, R and you use Fable package, or when you use, I don't know, Python with stat models or SCTime, or when you use reviews. So there is assumption behind. So assumption behind estimation that we are not only estimating coefficients, but we are estimating them in such a way that we assume that YT depends, implicit hidden assumption. YT depends on UT, UT minus 1, and so on. T minus 1 plus P2 YT minus 2 plus PP. Oh, I'm a little bit lazy. Okay, first implicit assumption that YT depends only on past values of U. Second implicit assumption that YT is stationary. But it's not always the case. For example, if you estimate ordinary regression, so it may be a shocking news for you that you are, maybe you were told that's a wrong statement, that if you estimate autoregressive P process by maximum likelihood and by regression, you will get the same results. No, you will not get the same results. They will be, let's say, the same for process that are close to stationary, but they may differ a lot for short non-stationary processes. So if I estimate, because when I estimate using maximum likelihood, these two implicit assumptions are usually made in procedures of estimation. And if I use ordinary least squares, these assumptions that YT stationary is not made. And sometimes the result may be different, but for short time series. Okay, I will not go into details how to construct a honest likelihood function. So the idea I need to, so my first point is about difference between equation and the process. Now, when we have grasped this difference, we may say not so much about Arima process. So let's go on. What is the definition of ARP process? So, so the problem is many authors, they either include or exclude the requirement for stationarity in the definition. So I will clearly state that ARP process is a solution of ARP equation that satisfies these two assumptions. That is stationary, and I will not copy the process. YT equals to phi1, YT minus 1 plus UT. So I have an ARP process, and I will say that, so I have ARP equation, and I say that ARP process is a solution of this equation that is stationary, and when YT depends only on past values of white noise, on UT, UT minus 1, UT minus 2, and so on. So that will be my definition of ARP process. Many authors, they are not so strict, and they say, oh, ARP process is something defined by this equation. But we need to be careful that equation is not a process. And by the theorem, we have only one or zero solutions of this type. So there is no problem to specify ARP process like that. Okay, let's move on. The problem with ARP processes, they are not so interpretable. If we speak about ETS models, the coefficients are interpretable. We can extract seasonality from them, and basically they're interpretable. We may say this is deseasonalized version of Y, this is seasonal effect. In ARP processes, they are not so interpretable. So it's difficult to interpret them. That's a pity, but bad news. Coefficients are not interpretable. They may be great tools for short-term forecasting, but we need to know that coefficients are not interpretable. I cannot say you how to interpret something like this, YT minus, I don't know, 0, 3 YT minus 1 plus 0, 0, 2 YT minus 2 equals to UT. How to interpret these terms, I don't know. So I may always say some artificial interpretation, and when YT minus 1 is fixed, then YT goes down by 0.2 if YT minus 2 goes up by 1. But this is nonsense, because how can I measure the influence of YT minus 2 keeping YT minus 1 fixed? So they are dependent random variables. I cannot fix YT minus 1, and I cannot increase YT minus 2 and just measuring the change of YT. So these coefficients are mostly non-interpretable. We can try to make some interpretations using partial correlations, but the sad news are that coefficients are not so interpretable. We cannot extract seasonal effects. We can model seasonal effects with Arima type processes, but not, we cannot extract them. Okay, let's move on. I need to, what do I need to do? I need to add Arima process. First Arima equation and then Arima process, yeah? What do I need for Arima equation? I will use lag notation because it's L of YT is YT minus 1, so I will use lag notation. But we should be careful about lag notation. Just a small check. Just a small funny exercise that we need to be careful with lag notation. If YT is X minus T, so I define YT and XT2 processes that are linked in this way. So Y1 is X minus 1. Y minus 1 is X1. Y0 is X0. And what is L of Y0 and what is L of X0?
L of Y0 is Y minus 1.
Okay, it's Y minus 1.
L
What
of
is L
X0
of
is
X0?
X plus 1.
Why?
Would we represent X and Y by some for instance, map processes or something like that. And we represent X or Y by some map processes.
I don't care about my process yet. It's just an idea that we should be very careful with lag notation. Be careful with lag notation. L of x0 is what?
X minus 1?
X minus 1.
X minus 1. But y0 is equal to x0. And this is y1. And these are not equal. Yeah? These are equal. And these are not equal. Why?
Maybe
Because
because
the process is the reverse.
maybe because like operator is just a linear operator and cannot like account for this.
It's linear operator, yes. And what's the problem with linear operator? Linear operator, I have applied linear operator on the same object, and I received different objects. What's the problem with linear operators? They are so bad. I thought that linear operators are good guys and evil guys. Okay, everything is fine here. Indeed, you are right that lag is a linear operator, but the subtle definition of lag operator acts not on random variables, but it acts on random processes. So basically, that's everything is correct. Lag operator applied to y0 and x0 will give us different results. That's okay, because it's a linear operator not on random variables, but on processes. And y process is different from x process. So lag operator, so honestly speaking, we need to have some notation like this. Lag applied to a process, let's say xt is, so we need to something like, this is a process x. What is the process? It's an assignment. For every t, we have assigned a random variable xt, yeah? And when we transform it, then we have another process that for t, we assign xt minus 1, yeah? So lag is a linear operator, but not on random variables. It's it acts on stochastic processes. So there is nothing bad that applied to, it seems, I have applied L to the same random variable. X0 is the same random variable as Y0. I have applied lag to the same random variable and I have received different results. That's completely okay, because we have applied lag operator to different sequences of random variables. If you consider a sequence of random variables, so this is t, this is x sequence, so -1, it's x minus 1, 0, it's x0, 1, it's x1. And we have applied, so we have one result. And if we use y sequence, if I write it in terms of x, it's x1, x0, x minus 1. So I completely clearly see on this picture that x sequence of random variables and y sequence of random variables are different. So when I apply lag process to different sequences, I have different sequences in the result, and there is nothing strange. So it seems, wow, I have applied lag to the same random variable and I have received different results. Yes, it may happen because lag operator is a operator applied to sequences of random variables. It's linear operator on sequences of random variables. That's a good point. That you may apply lag operator to the same random variable and have different results, different random variables, because the domain of lag operator is a space of stochastic processes and not the space of random variables. That's the first point. What else do you need to know about lag operator? So what else do you need to know about lag operator? Yeah. Any question? No, it's noise.
No more questions.
Okay. So let's discuss. We have a break. Okay, let's have a 10 minutes break. Yeah, 19. Yeah, it's a break time. Yeah, it's 30 or 40. Yeah, it's 30. Okay. Let's have a break. Let's finish with Arima and seasonal Arima process. Let's quickly discuss them, how to estimate in R using new syntax and how to estimate using all the syntax you will do in a home assignment. And basically that's all. Okay, if you have any questions, just don't be shy, ask them, and we will continue in 10 minutes. Yeah?
Sure.
Okay, bye for a moment.